Hi, welcome to tutorial 5 of organic analysis. This is the last tutorial in this topic, you'll be pleased to know. And this one is about testing for other functional groups, aldehydes, alkenes and carboxylic acids. So in the previous tutorial we've already had a look at how you can test for alcohols. So this is looking at all of the other tests. This is the tutorial that will go directly before your required practical and will outline the methods used to test for all of these different functional groups, which you're going to carry out yourself in the lesson. So the first functional groups that we're going to look at are aldehydes and ketones. So usually if you're going to test for an aldehyde, you would know that you've probably got either an aldehyde or a ketone. So perhaps you've tested for an alcohol and you have seen that the alcohol is oxidised by acidified potassium dichromate. So we've had the orange to green colour to show that you do have either a primary or a secondary alcohol, and then you need to know, well, is your product of that oxidation an aldehyde and therefore your alcohol was primary, or is it a ketone and your alcohol that you started with was secondary? So this is how you would test for the difference between an aldehyde and a ketone. Now, of course, it's important to remember the difference between an aldehyde and a ketone. So they're very similar, they've both got this carbonyl group. But with an aldehyde, the carbonyl group is found on a terminal carbon. It's found on the end carbon of a carbon chain, so the carbon chain would go along that way. And here you have a carbonyl group on the end, and that means that carbon's fourth bond goes to a hydrogen atom. That's the functional group of an aldehyde. A ketone is similar, it's got the carbonyl group, but the carbonyl is found in the middle somewhere of a carbon chain, maybe not directly in the middle, but it has carbon chains going off in one direction, carbon chains coming off in the other direction, and the carbonyl somewhere in between. So there are two methods I'm going to talk you through for distinguishing between aldehydes and ketones. The first one you should be familiar with is using Tollens reagent. So you will have done this before in lesson. And to begin with, you have to make the Tollens reagent up yourself. So you start by putting a small amount of silver nitrate into a test tube, a couple of centimetres cubed into there, and then you add a few drops of sodium hydroxide to your silver nitrate until you produce this brown precipitate. Next you take some ammonia, dilute ammonia, and you add a few drops of ammonia until you can get that brown precipitate to dissolve. Once it's dissolved, you now have a Tollens solution, a Tollens reagent. So Tollens reagent, the active part of it, is a diamine silver complex. So it's silver with two lots of ammonia ligands with a positive charge. And the idea behind the Tollens reagent is that the silver in the diamine silver complex has a positive charge to begin with, but these ions become reduced to elemental silver during the process if Tollens is able to oxidise your sample. So as we know, aldehydes can be oxidised. Aldehydes become carboxylic acids, which you've seen before with the acidified potassium dichromate. With a primary alcohol, it will oxidise to an aldehyde, and the aldehyde will further oxidise to a carboxylic acid. So we know that the positive result is going to be with the aldehyde, whereas the ketone can't be oxidised any further, so you get a negative result with the ketone. So once you have made your Tollens reagent up, next is to add some of your sample into the test tube containing the Tollens reagent. And then the Tollens and the sample are heated in a water bath for a few minutes, and when you go back and have a look at your test tube, you will see that if you have an aldehyde, you get a lovely silver mirror, if you're good at it. And if you had a ketone or you had something different that can't be oxidised by Tollens, you would have no silver mirror. Now, ideally, in terms of safety, rather than using a water bath that you've set up above a Bunsen burner, you are better using an electric water bath. This is because the aldehydes and the ketones that you're using in your sample are likely to be very flammable. So it is a bit of a health and safety concern, and you probably should be using an electric water bath rather than heating above a Bunsen burner. So just for your reference, here's a photograph of the Tollens test when it is positive and it forms a silver mirror, and when it's negative and there is no silver mirror, so the one on the left would contain an aldehyde, the one on the right no aldehyde. So we're now going to have a little look at a second method for testing distinction between aldehydes and ketones, and this is the one that you're going to carry out in your required practical. So the second method is using something called Fehling solution, which again distinguishes between an aldehyde and a ketone. So here we've got the equipment set up to show you how you would use Fehling solution to distinguish between these two functional groups. So Fehling solution is it's a little bit strange. It comes in two solutions. So you start with Fehlings A and Fehlings B, and you have to mix those two solutions together to make your Fehling solution that will actually work on your sample. So you don't really need to know the ins and outs of it, but the Fehling solution A is just a copper sulfate solution. So it's got copper 2+ ions in it. The Fehling solution B contains sodium hydroxide, and it is the reaction of the copper 2+ with the hydroxide ions that actually gives the test its positive result. However, in the sodium hydroxide conditions, the copper 2+ would just react straight away to produce copper hydroxide. So Fehling solution B also contains a substance called potassium sodium tartrate. And its job is to complex with the copper 2+ ions and keep the copper 2+ ions in solution so that it can react with your sample, and it prevents the copper 2+ from just reacting with the hydroxide straight away. So the most important part of this is that your Fehling solution contains aqueous copper 2+ ions. These copper 2+ ions are reduced if Fehling solution is able to oxidize your sample. So obviously if it's an aldehyde, it can be oxidized, so the copper 2+ is reduced, and if it's not an aldehyde, if it's a ketone, it can't be oxidized, so the copper 2+ ions cannot be reduced. So we've got the ionic equation across the bottom showing we've got copper 2+ ions, they are reduced to copper 1+ ions. So you take your Fehling solution, which you've just made up by mixing Fehling solution A and Fehling solution B, and you add to it some of your sample, which is an aldehyde or a ketone. Again, you leave it in a water bath. An electric water bath, again, would be preferable. And after a while, you go back a few minutes and you will see that if you have an aldehyde, you would get a positive result, which is this brick red precipitate. So that is the copper oxide coming out. And in an exam, just like in an exam about Tollens, an exam question about Tollens reagent, you would say a silver mirror is formed with an aldehyde, no change with a ketone. In the Fehling's test, you would say a brick red precipitate is formed with an aldehyde, with a ketone, there is no change. So here's a photograph just to show you what they really look like. This lovely deep blue solution, that is the Fehling's that's not reacted, so it was a ketone. And on this side we've got a brick red precipitate, so it looks like a brick red liquid, but you can probably tell it's a precipitate that's suspended throughout that liquid, and that is the copper oxide, showing that the copper 2+ has been reduced down to copper, showing that the aldehyde has been oxidized to a carboxylic acid. So the next test that we are going to look at is the test for saturation or unsaturation. So we're looking at the difference between an alkane and an alkene. So remember, an alkene contains a carbon-carbon double bond, and that is the definition of unsaturated. So this one's nice and simple, and you may have done it before. It's called the bromine shake test. So you take some of your sample, which may be an alkane, maybe an alkene, and you add to it an equal amount of bromine water, which really should be orange. It looks a little bit red, so I've coloured it in. So add an equal amount of bromine water. Obviously take care with all the health and safety precautions surrounding using bromine water, the vapours that come out of the bottle and things, make sure it stays stoppered when you're not using it. And then once you've added your equal amount of bromine water, you should stopper your test tube and give it a vigorous shake to get the bromine water to react with the sample, if it will. So if you have something that is unsaturated, you will get a reaction, and your orange bromine water, the colour that was in there from the bromine water, will disappear and you'll end up with something colourless. If you have something that is saturated, you will get no reaction, and because you've added orange bromine water into here, we say it remains orange. And please remember, if you're doing exam questions and they ask about a colour change, please say what it went from and to, not just what it turns into. So if you were talking about this test here, it goes from orange to colourless, not just it goes colourless. So for this one, you can know a little bit of background information. You should know it anyway about how it reacts. So I'll show you the mechanism for what happens when you've got unsaturation. So if we just look at the top diagram here, we've got an unsaturated compound. We've got ethene with its carbon-carbon double bond, and here we've got the bromine molecule, which is found dissolved in the bromine water. So in the test tube, as the bromine molecule approaches the carbon-carbon double bond, the electron density around the carbon-carbon double bond repels the electrons that are around this bromine atom and pushes them along the molecule. This means that down here is now partially negative, and the other bromine atom, which obviously did have some electrons but they've been pushed away, it leaves that with a partial positive charge. Now, because there's a large area of electron density here, this is partially negative and this is partially positive, so then you get an attraction. So you get electrons moving from the double bond onto this bromine atom, which is partially positive. The incoming electrons repel the electrons in this bond onto bromine, and you end up with the bromine atom that was here is now bonded to this carbon, and the bromine atom that's here is now a bromide ion because there's been electrons moved onto the bromine atom. So that's the bromide ion. Obviously you've got opposite charges again, you've got negative and positive, which are going to attract. So you get electrons moving from the bromide atom, the ion, onto the positively charged carbon atom, and that forms a bond. So your product is 1,2-dibromoethane, which is here, and that compound is colourless. So that reaction makes the orange from the bromine water disappear because the bromine's taken out of the water and is used in forming this compound here, which is colourless. So you get a colourless solution. If you were to try the same sort of thing with the saturated compound, there is no part of the alkane molecule with a large electron density. There's no part of this molecule that can induce a dipole into this bromine atom and actually cause part of it to be positive and negative. And if you've not got charges approaching each other, you're not going to get movement of electrons. So this one leads to no reaction. And therefore you keep the orange colour from the bromine water because it's still there, hasn't reacted. Okay, final test that I want to talk about is the test for a carboxylic acid. It's even more simple. It's something that you should know from GCSE. So in this test, you take a small amount of your sample that you're trying to test and you put it into a test tube using a pipette, and you add to it some sodium carbonate. So this could be sodium carbonate powder, as I've shown here, or it could be sodium carbonate solution. Doesn't matter, it'll still react with your sample if it's an acid. So if it's an acid, sodium carbonate would react with it and the reaction would fizz. You'd see bubbles, and if you add the sodium carbonate and there's no reaction, you don't see any change. So you should be familiar with this reaction along the bottom. So your reactions of acids, acid plus metal carbonate, such as sodium carbonate, will give you a salt plus water, which will give you a salt solution in here, and carbon dioxide, which is obviously a gas, which provides the bubbles and the fizzing. So to double check that, you could, if you wanted to, collect the gas that comes out of here and run it through some lime water, and you would see that the lime water goes cloudy. However, if you know that you're using a carbonate, you should be able to predict that you're probably making carbon dioxide. Now, obviously, the metal carbonate will react with any acid, so this is assuming you know that you've got some sort of organic compound that might be a carboxylic acid. Then it's the test for a carboxylic acid rather than just any other acid. So that's the end of that tutorial. We've gone through how to test using toluenes and phthalings for aldehydes, how to use bromine water to test for alkenes, and how to use sodium carbonate to test for carboxylic acids, along with your previous tutorial which told you how to use acidified potassium dichromate to test for acids. So you will need to consider how you could use these together, how you could use these along with other analytical techniques such as mass spectrometry or infrared spectroscopy, because that's probably how your exam questions are going to come across. Lots of clues from different analytical techniques to help you to determine what sort of compound you've got. So if you could go over to your Google Forms and complete your post-tutorial quiz, that would be great, and I will see you in the next lesson.